So I guess what I'm going to speak about is a little bit on the dynamics of rotating fluids. And these lectures might seem quite trivial to some of you who are familiar with rotating fluid dynamics, but I'm not really sure of the background of all the students. So we'll try to begin a little slowly, right? And I guess what I have as planned for lecture one, let's see how far we get in this, because we'll see how quickly we progress. It's to first of all put down the motivation, that is, we are interested in geophysical flows, and these flows are basically the flows of a large scale in the atmosphere and the ocean, right? And so two important features of geophysical flows are that one, they are influenced by the planetary rotation, and two, they are characterized by something known as stratification. That is, if you go outside and you measure, let's say, the density of air at the surface, and you repeat the experiment, let's say 3-4 kilometers up in the atmosphere, you'll find that the density changes, right? So it's stably stratified. In the same way, the density of the ocean varies with depth. Now, this is a equally important fact as compared to rotation, but given that we have only 4 lectures, I've chosen right now to suppress the effects of stratification. Maybe we'll get to them in the 4th lecture, depending on how quickly we progress. But for the time being, we'll only look at the effects of rotation on a fluid, okay? So once we have a rotating system, as you all probably know, we have to introduce a Coriolis force in the momentum in the momentum balance. And for the most part, in these lectures, in fact, all throughout, I will stick to Cartesian coordinates. One can work in spherical coordinates, but it usually just makes the calculations a little more messy. It doesn't really add much physics to the problem. So we'll work in local Cartesian coordinates, and there the effect of rotation is usually expressed through what is known as the F and the beta plane approximations. So we will introduce these two approximations and write down the set of equations, or at least the momentum balance that we get. Now, at this stage, I will diverge a bit. I will not go to the blackboard, but I will actually show you data and show you that if rotation is strong, what do we expect from it? And I will show you that you see this in data. That will give you a qualitative idea that rotation is actually important in the atmosphere and the ocean, right? And once we get this qualitative feel, we'll put it down in terms of a strength of a measure of the strength of rotation. So we'll non-dimensionalize our equations, and as with most fluid dynamical phenomena, the strength of rotation is measured by a non-dimensional number. This number is known as the Rossby number. We'll introduce the Rossby number, see how this matches with what we saw in data. Is that does the Rossby number in a particular regime imply strong effects of rotation, and so on, right? Once we have this, we'll basically say that, okay, we have to we'll have to settle on a set of equations to work with. We could use a very general set of equations, but what I will use throughout these lectures is something known as the shallow water equations, which are sort of the first thing that you use in geophysical fluid dynamics to explore any phenomenon that one comes across. And they really capture everything that one wants to know, at least at a first order level, with regard to rotation in a flow. So I will introduce the equations, and we'll see what we can do with them in this first lecture. The second lecture will basically proceed to analyze these equations in a little more detail. We'll see the conservation laws, linear theory, the kind of waves that are there, and most importantly, take the first steps towards something known as quasi-geostrophic theory, right? And lecture 3 is where I hope to introduce the QG equations to you. I hope to introduce something called the potential vorticity, which is sort of the backbone of geophysical fluid dynamics. And we will move from the F plane to the beta plane approximation, which is a little more general. And it, in fact, allows for the presence of a new class of waves, which are ubiquitous in the atmosphere. And these waves are also known as Rossby waves. So you see the name Rossby has already come twice. A Rossby number, a Rossby wave. Rossby was one of the giants of geophysical fluid dynamics. A lot of things are named after Rossby waves, Rossby number, there's a Rossby deformation scale, which also we will come across, and so on and so forth, right? Once we are done with this, I hope to go to the effects of nonlinearity in lecture 4, that is, what is geostrophic turbulence? So what happens when you take a system and you stir it, let's say, to a turbulent state, but it's also rotating? What do we expect from it? Do we expect a forward cascade of energy, an inverse cascade of energy? And how do these waves that are present in the linear problem interact with these nonlinear cascades? How do we form jets which are seen on the Earth or on Saturn, on Jupiter? Is there a universal mechanism behind them? So on and so forth. But this all depends on how we make progress in the first 3 lectures, right? So Let me start by putting this one picture up here. I will not talk about it right now. Just let's keep it up here, and we'll now move to the blackboard, okay? So, as far as we are concerned, the Earth is quite simply just a sphere. We'll not worry about the complications of its shape and so on. Just take it to be a sphere of some radius r over here, and it's rotating with a angular velocity omega. So omega is, you have your 2 pi divided by, let's say, 24.00. So approximately you get something of the order of 7 point. This is the speed that we have. And at any given latitude, say you choose a latitude phi over here, what we will do is at this point over here, we will set up a local Cartesian system. So for this point, you have, this is the local vertical going up. You have the direction j, which is pointing northward, and pointing inside the board is going to be the coordinate I, which is going eastward. So that is going to be a local Cartesian system that sits over here, right? Now, as far as this, your omega is going to be right? So you just have your three components, nothing in the I direction. You have something in J and something in K over here. And of course, as you all probably know, the Coriolis force let's call it Fc, is going to be minus 2 omega cross U. And my notation is such that U is equal to U V W over here, where U is in the I direction or eastward, V is northward in J, and W is upwards. That's going to be denoted by the vector U. So you have omega cross U, which is your Coriolis force. And I hope most of you have seen Euler's equation or the Navier-Stokes equation at some point, right? So if you don't have, so without rotation, we usually write the material derivative of U is going to be equal to the gradient of pressure, and plus if you have dissipation, you'll have some dissipative terms. This is the form of your of the three momentum equations for U, V, and W over here, right? So now when you include rotation, you basically are going to say that's all, right? So you get this extra term on the left-hand side over here, which is your Coriolis force. Now let's see what this works out to if you actually do the cross product, right? So let me come back over here. So if you do the cross product, in the x direction, you have d by dt of u minus partial x plus so on. You can just check this. Just do a 2 omega across u, substitute omega equal to this, where my f star is 2 omega cos phi, and let me call this a f naught, and your f naught is equal to 2 omega sine phi, right? This is what you will get. And similarly for the V equation, you will get plus if you have some dissipative terms, and in the vertical direction, and of course here you will have a G and so on, because you have the force of gravity acting downwards. So basically you get an extra term of the form Fv, Fw, F0u, and F star u. This is the effect of the rotating coordinate system or the Coriolis force on our fluid, right? Now, the question we want to ask is, if indeed rotation is strong, then what does this imply, right? And do we see it over here? If it does, then we have some notion at least that rotation is playing a role in the large, so this is the large scale structure of the atmosphere. All this is showing you is what happens in the month of July. You take many months of July, average them, this is the kind of map that you get. And this is showing you things at a very large scale. So do we get, or rather can we anticipate that from these equations, at least in a qualitative manner, right? So to do that, let me erase this. Where's the erase? Let me erase this part now. So the first thing we do is something known as the traditional approximation. And note that at the end of these slides, I will put up a set of references. So anything that you want to look up in detail as to how these calculations are done, or for example, how this approximation is formally justified, you can look at one of those references, right? So the traditional approximation basically says that these two terms, by scale analysis, are smaller than the rest of the terms in the equations. That is, anything involving cos phi, right? So this is the term that has the 2 omega cos phi with the F star, is neglected. And once again, if you want to see the scaling that actually leads to this, you can look up the textbooks that I'll show you at the end. So if you do this, what happens to, let's say, your x momentum equation is nothing but, right? And your y equation becomes partial y, right? So now you ask the question that, okay, let us say that the effect of the Coriolis force is strong. Strong meaning it's going to be strong compared to the convective acceleration of the fluid. So you say that these two terms are small, and the balance is basically the dominant balance is right here. So you say that if rotation is strong, we expect these to be small, and the balance will be between the Coriolis term and the pressure gradient, right? And if we assume this, that is, this is the assumption that rotation is strong, then what this implies should actually be seen over here. And this statement that I've put down over here, that is, Coriolis balances pressure gradients. This statement is known as a statement of geostrophic balance. And this is essentially the dominant balance at large scales in the atmosphere and the ocean, right? So what does this imply? That V is going to be 1 by rho times F0 partial P partial x. It's saying that the meridional or the northward velocity is going to be given by the gradient of P in the x direction. So note, the velocity in this direction is being given by the gradient in this direction. In the same way, U is going to be minus 1 by rho F0 partial P partial y. So the same thing, once again, the gradient in the y direction is actually telling you the strength of the flow in the x direction, right? So what does this mean? Well, let's take a synthetic example where this is my x direction. Let's say this, I've created somehow a high pressure over here and a low pressure over here. I create this and I let it go. So I create this, the fluid is at rest, I let it go, and the entire system is rotating. So I ask, if this is the dominant balance, what is going to happen? Well, initially, you all know that fluid is going to start flowing from high to low, right? From the high. So the fluid comes about, it's going to come over here. But in this region, the pressure is low. Here, the pressure is. So partial P, partial X is greater than 0 over here. What does that imply? You're going to pick up a V. So this fluid parcel that's moving here is going to start moving in a northward direction. In fact, if you trace this out, what happens as a consequence of this is that you will get a flow in this direction. So if the system was not rotating, the fluid would just go from high to low. Because of the rotation, the fluid actually goes around the low pressure system. In the same way, fluid will also go around the high pressure system. It will just move in a opposite direction. So here, in the northern hemisphere, because this is the sign that we have taken for F, flow that comes towards a low pressure actually circles around it in a anti-clockwise direction. This is the implication of this balance over here, right? Now, what will we have to change about this if you actually looked at the surface? The one thing that you would have to change is that near the surface, the flow is not going to be inviscid. It's going to be affected by frictional drag, right? So if you modify this and say that you have frictional drag, so in the x direction, it's of the form minus alpha times u. In the y direction, it's of the form alpha times v. So a simple drag on the flow. That means here, you will get an extra minus alpha u. You will get a minus alpha v over here, right, because of the drag. And you can convince yourself, if you go through this, try this as an exercise, that is, when you include these two terms, you will still get the same kind of motion, but with one difference. The difference being that if you actually look at the sense of the flow, that is, you take contours of the constant pressure, the flow will tend to go, that is, it will go in an anti-clockwise manner, but it will try to spiral inwards because of the effect of friction. In the same way, if you take contours of high pressure over here, you will get flows that are moving in a clockwise direction, but they will actually tend to go, they will try to spiral outward. So from the high, you get systems that spiral outwards in the northern hemisphere. In the low, you get systems that spiral inward. This is what you expect from very simple qualitative balance between these terms. Now we say, what do we see? This is the map of sea level pressure and the velocity fields in the month of July. You have averaged many Julys. Look at, say, for example, the Pacific. You have a huge high pressure system here, another high pressure system here. These are sometimes called the subtropical highs associated with the atmosphere. They have names such as the Hawaiian high and so on that you don't have to worry about. But look at that. Around this high pressure, you have a circulation that's clockwise, and moreover, it's crossing the contours and spiraling outwards. That's exactly what you expect from a first order picture over here, that around the highs, you're going to get stuff that's going in a clockwise direction, but it has a tendency to spiral outwards. That's precisely what you see over here, right? And you can also look in the southern hemisphere, you have the same story, excepting the sense of circulation flips because F has become minus F, right? Your rotation rate is gone to the opposite direction. So you see exactly the same kind of thing, but instead of a clockwise circulation, you have an anti-clockwise thing that's spiraling outwards. That's what you get in the southern hemisphere. Another interesting thing about this is, what about India? This is July. What's going on in India? The monsoon is on. What do you have over India? You have a large-scale system called the Tibetan Low that sits here. So what is the sense of circulation? You expect the circulation to be anti-clockwise and spiraling inwards. So this is consistent with the monsoonal flow that's coming in. So you have anti-clockwise circulation going here that's spiraling in. That's consistent with the inflow. In fact, it's part and parcel of the monsoonal system that brings moist air from the Arabian Sea and so on into India here. Right? So that's what we see during the month of July. If we go ahead and we flip this to the month of January, you basically see that things get reverse. That is, the high pressure system that was here has actually got squeezed down. It's come from the subtropics into the tropics. The high pressure system from here has also got squeezed down over here. It has been replaced by a low. And now For the low, you expect the circulation to be anti-clockwise, spiraling inwards. That's exactly what you see over here. Low, spiraling inwards. This guy is a little more messy because you actually have two lows that are sort of fighting with each other. So the circulation is not as clear as what you see over here, right? But so the one thing to take away is that if you just introduce the Coriolis force at a very basic level, yeah. So this, I think, is just reanalysis, which is a fancy word for a model plus data. So what people do is they run a general circulation model, but they also have actual data that's measured at points. So these simulations are guided by this data, and they usually run in hindcast. They're not a they're not a forecast. So this will give you, let's say, a correct representation of the atmosphere last year. And it's through all kinds of data plus a model. That's why you get the whole globe. If we just use actual data, it would be much more spotty, and you won't have anything over the oceans, really, right? Yeah. So the one way to see it is usually these equations are for an atmosphere, which is a very thin layer on top of the Earth, right? So the scale in which the motion is taking place in the horizontal direction is much larger than in the vertical direction. So the W is actually much smaller than U and V. So what ends up happening is, because F comes with W over here, you say that this term is going to be much smaller than these two. And for consistency, you neglect this guy. Otherwise, you get into trouble if you neglect this and you don't neglect this. Exactly, so that's why, so you don't neglect this from the start, you neglect this, but for consistency, you have to neglect this guy. So the way in which you do it is clearly spelled out in one of the references I'll show you. Basically, non-dimensionalize the equations, and you go through the other argument, right? But note that in numerical models these days for the weather and so on, they don't do this. It's actually there. So this traditional approximation is an old approximation that was made. It's nice for our qualitative balance, but in most sophisticated numerical models, the whole term is there. There's right. So yeah. So geostrophic approximation is actually very good, but it is very good when you go to the mid-latitudes, right? Because you need F naught to be present, right? What is F naught? F naught is 2 omega sine phi. So as you come closer and closer to the equator, you expect geostrophic balance to become invalid. So really, these things are going to be valid in the mid-latitudes, and that's exactly where you see them, right? You see this stuff is actually not in the tropics, right? If you go from 20 to 20, you really don't see geostrophic balance. It's out here at 30, 40 north is where you start seeing geostrophic balance.
At the north and the south pole,
sure.
U and V velocities, one of them is going to blow up.
Right, so that's where you usually don't use a Cartesian system then. So if you want to actually model the whole globe at once, you would not use this kind of a system. You would actually use spherical coordinates. You would not use this. This is fine for a local patch that's at some latitude 5, where you're not expecting the motion to be too big. So it's not coming too close to the equator, so F naught doesn't go to 0. It's not going too close to the pole. So you're basically saying we are on a patch there, right? But you're right. For the entire globe, we definitely have to use the full spherical coordinates and so on. Yeah? Anything else? Yeah. Excuse me?
What causes the high pressure?
So that is something that, so once again, these high pressure and low pressure systems are there because the Earth is rotating. See, these are nothing but, I guess I'm jumping ahead, but this was the exam. These were some of the examples I was going to show you later on. These are nothing but stationary Rossby waves. They are caused because what you have in general is, you have a jet that's going from west to east. But that jet is going to encounter some obstacles. What are the main obstacles it encounters? Well, you have the Himalayas and the Tibetan plateau here, and you have the Rocky Mountains here. These are very, very high mountain ranges which these jets come and impinge upon. What's going to happen if a jet comes and hits an obstacle? You're going to set up stationary waves. Those stationary waves are nothing but Rossby waves, and they critically depend on the rotation of the planet. So these, as you have rightly seen, the structure of this guy is actually intimately connected to the rotation of the planet. They would not have this structure if the planet did not rotate. So you see, you're getting, not only is the guiding line rotation, the system itself is also influenced by rotation. So it's a double, yeah. See, so right now I'm saying that we are not considering the effects of stratification at all. Really, this rho should be a function of, strongly of a function of z, right? So if you actually want to compute this kind of a response and you use the equations that we will use, that is the shallow water equations, you will get an approximation to this. But if you want this kind of a structure, you have to use the stratified equations, because you're right. The fact that the equation that the atmosphere is stratified does affect the shape of these guys, right? But at first order, we will get away by neglecting that, right?
And what is the red line?
Which one? Oh, so I guess you saw that. Okay, so that, let me go back to the previous slide. So that red line is something known as, so it's written over here, that's called the ITCZ. So this is something known as the intertropical convergence zone. And this is basically where you have, so if you look at the winds and you look at where you get the most of the rainfall in the tropics, this is where the flows converge, rise up, and then diverge. So that's why it's called the intertropical convergence zone. And if you can see in the monsoonal time, this convergence zone has moved way here. And in fact, most of the precipitation occurs just before the convergence zone. So you expect a lot of convergence to be taking place here, rising motion, and then coming back. Whereas if you go to the other season over here, oh, where did that go? Your ITCZ has come all the way to the south, and the flow is in this direction, so you don't expect any convection to take place over here, right? So this is, in a sense, a place that marks the maximum precipitation that you get on the planet. Because, see, all these things are basically moist, right? And as soon as they converge and they uplift, this moisture gets rained out. So this is a crude measure of where you expect the rainfall boundary to be. Right? You won't expect any rainfall to be beyond this in the tropics. In the same way, in this case, you won't expect any rainfall beyond this over here. You would expect all the rainfall to be contained on the equatorward side of this guy. Right? So that is a first order picture of what the ITCZ gives you. Right?
So it's not like a jet stream or...
No, so this is, so we are all on the floor. So the jets and all are very weak on the floor. The jet streams are much stronger when you go up, right? Oh, so what is the time? How? Half an hour. Okay, fine. So what do I? Yeah. So yeah, so the sign of F, yeah.
So does it not cause problems if two high pressure regions are close together near the equator?
Sure. So it's very difficult for parcels to actually cross the equator, right? Because they so this is something we'll come to when we look at the conservation laws of the system. You will find that there is one particular conservation law which is called the material conservation law. So it's something that a fluid parcel conserves as it moves, and this is actually related to the vorticity of the parcel. It's something called the potential vorticity. So when you move across the equator, what you end up doing is you have to have certain kinds of dissipation to allow your PV to change. Else, a PV conserving flow would not like to cross the equator. It will in fact try to come back, right? Yeah. So this is mainly, in July, what happens? You are in the northern hemisphere summer, right? And northern hemisphere summer, the Tibetan low is basically, you have high mountains here, or a big plateau, which is heating up. So as compared to the neighboring air at, let's say, 5 kilometers height, the Tibetan plateau is much hotter than the air next to it. So that's why the low that you get over here is situated a little bit to the south of the Tibetan plateau itself. But when you come to the Siberian high, that's actually governed by what is the landmass over Siberia, not what's going on over the Tibetan thing. That's why it gets moved a little to this side. Now, if you ask me why this guy is displaced a little bit, and whether this is actually the cause of all monsoon, you're getting into problems that people are not very comfortable with. In fact, there's very, very recent work that is still trying to figure this out, as though where is the cause and where is the effect, right? What is the monsoonal flow, is the monsoonal flow building into this, or is this basically the monsoon, that you get a low and it pulls air in and that's the monsoon? So there are various views on this, which I guess we don't have the time to get into, but if you want to discuss them, whatever I know about them, I can tell you, right? So, okay, so we're here, okay. Now, the one thing that I want to see from this is scales, right? Because when we actually look at these equations and we'll do a non-dimensionalization to get the strength of rotation, what it'll involve is, it depends on what scale you're talking about. So what are the scales here? This low pressure system, say for example, which we see obeys what we would get from geostrophic balance. What is its size? It's spanning basically all of the Pacific, right? So what is the width of the Pacific? Of the order of 10,000 kilometers or so, right? So you have a 10 raised to 7. That is the size over which geostrophic balance seems to hold. Same way, if you look at the other ocean basin, well, this guy is also of a similar size. All the whole Atlantic is being spanned. Might be a little smaller than the Pacific, but you're talking of scales from 5,000 to 10,000 kilometers. So really, really large scales, right? Now, is geostrophic balance only useful at such large scales? Well, let's look at another example. This is actually data from a weather map, which has been smoothed over, I think, 2 or 3 days over the US. This shows you basically a similar structure. That is, over the eastern part of the US, you have a low around which the circulation is anti-clockwise and trying to spiral in. Over the west coast, you have a high, so the sense of circulation is over here, and it's spiraling outwards. So you get basically exactly what you expect, but at a completely different scale. What is the size of the US? It's about 4,000 kilometers across. So each of these guys is approximately half of the US, so the scale of this is barely 2,000 kilometers. So what we saw was true at a scale of 10,000 kilometers is also actually true at a scale of 2,000 kilometers, right? So what we are seeing is that this kind of a balance is actually holding true once you go to scales that are a few thousand kilometers and more. You go to 1,000, 2,000 kilometers, you start seeing the consequences of geostrophic balance, all the way up to the largest possible scales of 10,000 kilometers, right? And of course, this will get formalized when we write down the Rossby number, right? What do I have next? Oh, so we'll come to this a little later. Yeah. Exactly. So that's what will come in when we do the
material derivative term over there. So that would have u dot grad u, right?
Exactly.
So that would how you can no longer neglect it on such larger scales, right?
So what we are saying is, if that term is smaller, then this is the balance we expect.
Scales you're talking about there, the grad u would be u dot grad u would be important, right?
Right, but it's still smaller than this. That's what it's telling you, right? So if u dot grad u was as strong as this, you would not really see exactly the consequences of geostrophic balance, right? So what it's telling you is that up to scales is from scales of about 2,000 kilometers onwards, these two are stronger than this term over here.
How do you decide that?
So that's what we'll come to, right? When we actually follow that, we have to actually do the mathematics. This is more qualitative. So when we actually do the non-dimensionalization and introduce a Rossby number, that's exactly where you will see the role of u and the role of the length scale, right? So they are tied to each other. So let's do that. Now we are here. I guess we can start off on, we can erase this, I guess. Yeah. Right. So yeah.
When you see circulating winds around here, is geostrophic balance valid there?
So you can decide for yourself when I write down the Rossby number, okay? So I'm sure that non-dimensionalization will be done in a much more proper manner, say by John Luke or Savdapaman, who's going to deal with mixing. It's very important there. Also in turbulence, I will do it in a very, very quick way, something that will get us to the Rossby number, right? So the idea is, for those. So you take a dimensional variable, say you're dealing with the length x, you take it to something of this form over here, where this is a non-dimensional measure of length, and L is sometimes referred to as the scale parameter. So for example, let's say we have a tank of size of this table, there's a fluid in it, and we want to study its dynamics, right? Naturally, we expect the length scale of the table to have something to do with the flow, right? So we would say, okay, I'm going to choose my L to be the size of this table, right? And then what ends up happening is this guy absorbs the actual measure. That is, it takes the value of, let's say, 1 meter, 2 meters, so on, and this guy is of order 1. Right? So, for example, if you were going to non-dimensionalize this problem over here, you're interested in weather over the US, right? And you're given the Navier-Stokes equation. Somebody says, what is the appropriate length scale to use? Well, you see that on a weekly basis, you get highs and lows that go across the country that span approximately half the width of the country, right? The width of the country is 4,000 kilometers or so. So appropriate length scale, if you are interested in focusing on these kinds of systems, would be to say L is 2,000 kilometers, 2,500 kilometers. That would be an approximate scale that you would intuitively use, right? That's precisely what guides these kinds of choices. And of course, you immediately note that non-dimensionalization is non-unique. You can non-dimensionalize an equation in different ways depending on what you're interested in. Right? If you're interested in large scales and slow motions, you'll choose U to be small and L to be large. If you're interested in very fast, small scale motion, you'll focus on a very small length scale with a very high, with a very short time scale, right? So you can have non-unique non-dimensionalizations of the same equations. In fact, that is the art of non-dimensionalization. People who have intuition for non-dimensionalizing things will choose the best non-dimensional scale that's there, and that will illustrate the problem to you. We go because we know the answer. That's why we'll choose the scales over here, right? So this is your x over here. In the same way, we assume there's no real difference between u and v. Really, you could choose a different non-dimensionalization for Lx, Ly, for the meridional velocity, zonal velocity. Right now, let's treat them all to be the same. U and v are going to go as some capital U times u tilde and v tilde. These are your non-dimensional guys over here. And if I fix a L and a U, I can basically take a non-dimensional time scale to be t, right? So my time is going to go to this t times t tilde over here. Now note, because you're on a rotating planet, what is another choice for t? Instead of you using L by U, what could you choose? A natural choice would be 1 by f. Right? Your planet is rotating, so that is a rotation rate you're imposing on the problem. So you could say, well, I'm interested in that time scale, so I'm going to choose my t to be 1 by f. That would focus on motions that occur at the time scale of 1 by f. Right? This thing is going to focus more on motions that are associated with the specified length and speed over here. Right? So you have your t, you have your u, you have your x, and let's see the x momentum equation. Right? Let's forget dissipation for the time being, and we are over here, right? Now, what we have said is u is going to u tilde. So basically, you're going to have this is going to be the first term over here. Plus, all of these are going to go scale in the same way because we are assuming u, v, w, x, y, z to be the same thing. You can choose them to be different. For the time being, we'll keep them to be the same. So this is basically going to go as is just u dot grad u in non-dimensional form. They'll all have a u squared by L associated with them. What about this guy? Well, f naught is just a number. V is non-dimensionalized by u is equal to, in the same way, you will put a, let's say this is non-dimensionalized by rho naught, and the pressure is non-dimensionalized by P. This is a L, so you get a partial P, partial X, right? So you basically said rho is going to rho naught times, somebody's, which one? This one. So that's why you've got a, exactly. So yeah, so they're all tildes. Yeah. So basically, you can say that if everything that's here is a tilde, right? So now, this is your prefab factor over here, right? So now, what is t? T is the but L by u. So once again, this takes a form u squared by L, right? All you do is you divide by a u squared by L. So basically, you have So let me just write this whole thing as right? Where so this is going to be P by rho naught L, and you get a this guy. So this is sometimes known as the Euler number, and this is really the number that we are interested in because this is what quantifies the strength of rotation. So what has happened to our rotating term is that you have not dimensionalized it. So this is of order 1 over here. Right, this is of order 1. Its a prefactor is 1 over the Rossby number. So you can say that when the Rossby number is going to be small, this ratio is dimensionless. Right, UFL is dimensionless. When this ratio is going to be less than 1, this term is going to be strong. So rotation is strong when, let me write it here. Okay. So when rotation is strong, you have Rossby equal to U by F naught L. If this is less than 1, you expect rotation to be strong. And when Rossby equal to is greater than 1, you expect the rotation to be weak, right? That's exactly what this guy here is telling you. Now, you can interpret the Rossby number in multiple ways, right? So here is where your question comes in, is that it's not only the length scale, it's also the fluid velocity, right? So if you have a particular length scale and your U changes, it could vary. The influence of rotation can vary, right? So let's try to verify it for some of these systems over here. The first thing we looked at was this guy, right? So what is the scale of this? We said the scale of this is approximately 10,000 kilometers. Your F naught, if you're, let's say your phi is approximately 45 degrees, so your F is about 10 raised to minus 4, second to the minus 1. So what is Rossby? Is going to be U by 10 raised to minus 4 into 10 raised to 7, right? So this is basically U by 10 raised to 3. Now, obviously, the speeds of these guys are nowhere near 10 raised to 3. In fact, near the surface, the speed is more like 10 meters per second is the upper bound that you will get. So if you put U equal to 10 meters per second, you're going to get this is approximately 0.01, which is much less than 1. So in fact, these subtropical highs are strongly controlled by the presence of rotation because the Rossby number is in fact very small. Right? You can do more examples of this kind, and this is where I have the next slide. What about this? What do you guess? Do you think for hurricane, a Rossby number is going to be large or small? Is rotation important or not? Well, just by looking at its structure, you can probably say that yes, it is going to be important. This is a picture of Hurricane Sandy, which was a couple of years back. Look at its size. It's spanning pretty much half the coast of the US, right? So a length scale of approximately 1,500 to 2,000 kilometers, wind speeds of the order of 30-40 meters per second. Once again, you're in the mid-latitude, so F is of the order of 10 raised to minus 4. If you plug in those numbers over here, so for a hurricane, you will find that the Rossby number works out to approximately 0.5. So it is still less than 1. Not as small as this guy over here, but it is still less than 1. That is, rotation is playing a role, and that's exactly what you see over here, is that a hurricane is a low-pressure system. In the northern hemisphere, what do we expect? Winds that are spiraling inwards. That's exactly what you see. These are the spiraling rain bands that are come up in over here into the low-pressure system. The other thing that you can see is the track of a hurricane. How does a hurricane move? Well, where are these hurricanes that hit the US born? They are born in the Atlantic over here, right? And they're usually born, let's take this guy. So they're born over here. What's going to happen? They're going to move this way, and then move out. And that's usually the climatological track of most hurricanes. So not only is their path guided by these high pressure systems, which in turn are governed by the rotation of the planet, their internal structure itself, that is, over here, this kind of a structure is also influenced by rotation. Now, one of the complications, you can take another example. Say, for example, this is Irene, which was a year prior to that, a similar structure, same length scale, little smaller than San Andy, but again, the spiraling air that's come up here, right? So, based on this, you might actually say, well, predicting the track of a hurricane is trivial, right? I know that my high pressure is here. Anything born here has to go over here, right? The problem is, when are these hurricanes born? If you look at the dates, this guy was in October. This guy was in August. That's pretty much exactly the time when you are transitioning from this pattern over here in the summer to this pattern in the winter. So these high pressure systems that are there are gradually weakening and moving towards the equator, towards a winter time cell, right? So you don't know exactly what the structure of the high pressure cell is. So the hurricane that's born here, you don't know whether it's going to go and hit this coast here, whether it's going to come down here, because that high pressure cell itself is changing in character. That makes the track of these guys somewhat difficult to predict, right? And the same thing holds true in the Pacific over here. The typhoons that come toward Japan, it's the same story, right? They're born over here, and they basically come, and we are in the wrong season, right? So they come over here, and they hit this. So, and you see that they're only there during the summer time, because that's when the flow is of this character over here, right? So that tells you that for a system like a hurricane, your rotation is going to be important. Now, what about this guy? This is a tornado. You can look at its scale. Its scale it's far from this house, but it's of the order of a few kilometers. Right? At the most, the scale of this guy is 10 kilometers or so. But the speeds in a tornado are comparable to a hurricane. They're about 40, 50 meters per second, even more. If you do that calculation, that is, you do U by FL, but now you say U is, let's say, 50 meters per second. Your F is 10 raised to minus 4, and let's say your scale of this guy is 10 kilometers at the most, right? So this is going to give you a 10 raised to 4 over here. This is going to be approximately 50, which is much greater than 1. So the rotation of a tornado really has nothing to do with the Coriolis force. It's mainly rotating because of the shear in the winds. That's how it's created, and that's what gives it its rotation. Whether it's in the northern hemisphere or the southern hemisphere, its sense of rotation is not going to change. It's not influenced by the rate of rotation in a planet, right? Same way you can do the famous example that people keep putting up, that is, the water in your bathtub moves in the other direction in the southern hemisphere. Is that true? What would happen? Plug in the numbers, right? U is what for the bathtub? Barely of the order of a few, at the most 1 meter per second. That will be a really fast bathtub, but still 1 meter per second. F is about 10 raised to minus 4, and your length scale is barely 1 meter, right? Or at the most 10 meters, a huge bathtub. Even with that, you're going to get a Rossby number that's very, very large. So the motion of your fluid inside the drain has nothing to do with whether you're in the southern hemisphere or the northern hemisphere. It's more the geometry of the drain. You could probably get it to go which way you want to by just making the drain geometry slightly different, right? So you can answer your question. If you have typical numbers, you can check. That is, if you're talking about a field where you have a scale of 10 kilometers and flows of the order of a few meters per second, it's unlikely that they're going to be affected by the rate of by the planetary rotation, right? So another way to look at this is, what are we talking about? This is the ratio of U by L to F naught, right? So F naught is a sense of rotation or vorticity that's being given by the planet, right? What is U by L? U by L, if you look at omega, which is the vorticity, is equal to del cross U, right? So basically it's U with a L in the denominator. So the scale of the vorticity is of the order U by L, right? So what this is really measuring is the relative vorticity of a parcel to the vorticity imparted by the entire planet. And if the relative vorticity is much greater than the planetary spin, then the parcel doesn't care about the planet. It doesn't matter if the planet is rotating, because it is spinning in such a fast manner that it really doesn't care about the planet. On the other hand, if the vorticity of the parcel is comparable to that of the planet, then it starts talking to that. It sees that rotation. If it's too fast, it doesn't really care, right? If it's slow enough, the sense of rotation, that's when it starts caring about the fact that it's on a rotating coordinate system, right? So that's the rough idea of this guy over here. Now, I guess I have only 10 minutes. Let me try to just put down. So this has basically been a qualitative this thing of why rotation is important in the atmosphere. That is, we said, if there is rotation, you're going to put a Coriolis term. Let us assume it to be strong, you get some balances, right? And those balances are actually seen in data. And then we try to see, well, can we quantify the strength of rotation? We get a measure for it, which is a non-dimensional number. Now the question is, if we actually want to study precisely these kinds of system, that they're a very difficult system, but let's say you want to study these kinds of lows and highs, what are the set of equations that we would use? We are going to have to put down, agree on some set of equations. And the equation that I'm going to choose for this set of lectures is something known as the shallow water equation. So let me write them down. I will, the references that I'll put up have detailed derivations of these equations. Yeah.
Geostrophic balance.
So right, so when you have, so in the overall equations, when the pressure gradient is balanced by the Coriolis term, you have a geostrophic balance, and that is what we expect. If
only looking at Rossby number, then what about that dimensionless number that we left out?
Right, so see, in this equation over here, right, if, let's say, rotation is strong, then this guy has to be solved.
To be compared.
You're sure, right? So we should also compare it to this. So usually, actually, we have another term here which also brings in friction, right? So usually, if you want to do a more clearer analysis of this, we will bring in Rossby, Euler, as well as something called the Ekman number, which will measure the strength of the friction. But at a very crude level, if you forget this part over here, you say, well, if you want rotation to be strong, first of all, this needs to be strong. That's the first ingredient. You can have more constraints that come from here. That's right, right? But the first order constraint is from here, right? Yeah. Which, actually, can you repeat what you're saying?
Spiraling structures we were getting by this, neglecting that capital D by dt term.
Right, right. So we are saying that if this balance holds, that is, you have friction, you have the pressure gradient, and you have Coriolis, then what you expect is that the flow would go in this manner and it would spiral inwards.
We sort of incorporate those two terms which we are doing now.
Sure.
Justified to expect the same shape, the spiraling shapes.
Right, right. So what will happen is that if you, so see, for example, if you want to consider the evolution of this guy, right, from one time to the other, with this, you can't do anything, right? This is just a diagnostic balance that tells you if the pressure gradient is so much, if geostrophy is strong, I expect the velocity field to be in this sense. But there's no way in which you can predict what's going to happen at the next time step.
The evolution.
Exactly. So for the evolution, you require these guys, right? So even though they are small, they are what control what happens in the next time step. And that's precisely, in fact, that is the point of quasi-geostrophic theory. The whole aim was, people said, you observe geostrophic balance, but we can't evolve it. So what do we do? And this is where the mathematical analysis came together with the physics to say, let's develop something called quasi-geostrophic theory, which is in fact the evolution or the temporal evolution of geostrophic balance. And it involves these terms.
That can be justified with the first term, del U del T. But what about the U dot grad U term? That doesn't really show the evolution, right? What exactly?
So it will show how this system will move, right? The convective derivative is involved in the translation of the system, right? So you want, basically, let's say you want to do the weather prediction of this guy, you will have to get all of those terms in, right? So of course, nowadays with sophisticated or more stronger computers, you don't really care about what is important and what is not. You can just put the whole thing in, right? But from a physical point of view, the balance is basically here, but the evolution is coming from the small changes that you have. That's what pushing the guy along. And that's precisely what's captured by QG theory. And hopefully, we'll be able to derive that in the next class or two, right? So I guess, OK, so there are a couple of minutes left. Actually, let me just stop. Instead of trying to write these down in a haphazard way, I'll start the next class by putting down the shallow water equation. There are certain basic assumptions involved in these equations which might look very, very strong. But it so turns out that the shallow water equations are extremely useful in GFD, in geophysical fluid dynamics. So we'll write them down and we'll progress to our conservation laws and linear waves and so on. And I'll just leave you with this, I guess, what was the? Right, so these are some of the textbooks. Most of these, if you want, I can give you PDFs of them. I have most of them as PDFs, and I guess you guys know better than I do how to find PDFs on online. So these are basically the classic textbooks on GFT. The first one is by Cushman Royson, where the part 2 of the textbook basically looks at what are the effects of rotation on a flow. That is, take the density to be a constant, just make the flow rotate. This is what you get, right? Similarly, the classic textbook nowadays is a textbook by G.K. Wallace, which was, I think, it's about 10 years old. It's a beautiful textbook that has the derivation of the water equations that we will just write down in the next class. The waves that we will talk about are done in detail, all the conservation laws, and so on. The classic book is by Pedlowski, which is a little heavy duty because Pedlowski likes to do everything that is possible about a particular problem. So it's a little big, but chapter 3 in Pedlowski is basically all about the shallow water equations, right? The whole chapter on it. The more mathematical view for people who are from a more mathematical background is a textbook by Andrew Maida, which is partial differential equations for waves in atmosphere ocean science. So all these justifications, they require mathematical justification. If you're going to derive the QG equation, can you formally prove that solutions of something converge to something else? Those kinds of things you will find in this book over here, right? And the two older classics, one of them is Atmosphere Ocean Dynamics by Gill, which is probably the best written book. It has the most physics in it, in a sense. He has the best physical feel for most of the effects of rotation, stratification, so on. It's a little old now, but it is a very, very nice book. And same way, the book by Holton is one of the classics that was written in the 80s on dynamical meteorology. It still remains a classic. There are newer editions of it, but these are sort of more slightly dated. So, I mean, you can refer to them. All the material we do will definitely be present in these two also, right? But really, 1 and 2 are the first two are the things that you can look at, right? Okay, so we'll stop here, and next class, I guess we are on Wednesday, right? I think it's Wednesday morning. Okay, so Wednesday we'll start with the shallow water equation, okay? Thanks.